So the last question is example 20, and it says, for each of the following real-life situations, state if it can best be modeled by an exponential, a logarithmic, a linear, or a quadratic function. Don't say none and then come up with some philosophical excuses. Just tell me one, okay? So the only thing you have to write for each of these problems is exponential, logarithmic, linear, or quadratic. We just want the word. Now, the upside is you don't actually have to build the models to prove your point. The downside is there isn't a lot of partial credit on this. So this is a very important question because we need to understand if you understand how to build all the models from the last exam and the next exam, and FYI, on the final, it's cumulative, so you better know how to build models. So here we just want to know, can you identify the scenarios that dictate the model? So just to show you that I'm correct on each of these assumptions, I am going to show you how you can very quickly logic out the correct model for each scenario. So you come to a casino with $500 and you play blackjack. You bet $10 on every hand and lose every time until the money is gone. So what kind of function best describes your money as a function of time? So if you don't see this, right, your money is going to be based, right? Time is really every hand you play. So right, time is the length of time you've played, but we can also model it based on, well, every hand I'm going to lose some more money. So you're going to start out, right, with $500, and then after you play one hand, you're down to $490 because you lost $10, and then you're going to lose $480, and then you're going to be down to $470, right, $460. So you keep dropping the amount of money you have by $10. So hopefully this looks like a linear relationship to you, because lines, right, and if we actually wanted to graph this, right, we would see this happening. We start with 500 and then we're dropping by 10 every hand we play. So this represents a linear relationship. You're losing the exact same amount every single time. But all you would be required to put on this question is linear. B says you come to a casino with $500 and you play blackjack, but you bet half the money you have left on every hand and lose every time until the money's gone. It says, what kind of function best describes your money as a function of time? So once again, we're going to model this, right, where we're talking about the number of hands. And now I start out with $500, but then I bet half of it and I lose, so I'm down to $250. And then I bet half of it again, so I'm down to $125, right? And then we would bet half again. So what's happening now is this is an exponential function, right, where your money's cutting in half every time. So I could actually write a function where I said I start out with $500 and then I reduce the amount by half every single time. So we can clearly see that this is exponential, and it's actually exponential decay, right? But we only have to give the model. So once again, that's the only thing required. I'm just showing you to justify how I knew it was exponential. So you may not always be able to write the equation, but sometimes just listing out the values if you know how these graphs behave. If we plotted this, right, we'd see we have 500, right, then we're down, then we're down, then we're down, and would start cutting in half. And so you could also kind of look at the graph and come up with exponential. C says you want to build a circular enclosure and fencing costs $2 per linear foot. What kind of function best describes the area of the enclosure as a function of how much money you would spend? So a circular enclosure, right, the amount of fence you would need is going to equal, right, the circumference of a circle, which is 2 pi r. So no matter how big your circle is, right, we need 2 pi r worth of fencing. The cost of the fence, right, is going to be $2 per foot times the amount of feet you need. So now what it says is, what kind of function best describes area as a function of cost? So area in terms of the radius, right, is pi r squared. So if I come back over here and I solve my cost for r, right, cost is 4 pi r. So if you divide it over, well, I can see this is a quadratic in terms of r, but now if I replace r with c over 4 pi, then the c will get squared, and I still end up with a quadratic. So this is a quadratic. Most of these area functions are going to be quadratics, because if you think about it, right, the units of area are meter squared, square feet, right? So it makes sense that you would use a quadratic to find the area of something. D says you are staging an athletic tournament. Every round you pair off all the teams and the losing team, or every round you pair off all the teams and the losing teams are eliminated. So this is a single elimination tournament. You lose and you're out. Let X be the number of teams in your tournament and let Y be the number of rounds that needed to be played for the championship game. What kind of function best describes Y as a function of X? So you want to make sure when you're reading problems like this that you're reading the model they want you to build. So in this case, X is the number of teams, and we're told Y is the number of games, okay, or rounds. Sorry, number of rounds. And we want to know what kind of function, right, is Y as a function of X. So that means I plug in the number of teams that are left and the number of rounds that needed to be played comes out. So this actually isn't a very intuitive way to build a function, but if you know anything about sports, there's a perfect example for this, and that's March Madness, the NCAA tournament. We start out with, I think, 64 teams now. It used to be 32 teams is round one. And you pair them off in twos, and every team that loses is out. So then we have the round of 16, right? The Elite Eight, the Final Four, right? The semifinal, and then the final. So you can see that each time we play a round, the number of teams is cutting in half. And this actually sounds a lot like our blackjack example that we did earlier where we were betting half the money. So the easier way to set this up would be to say, well, I know that if I start out, right, with X teams to begin with, because X is going to be the number of teams, so I'm just going to call that X naught, right? Every round I play, the number of teams reduces in half. So for every round, right, the number of teams I have is the number of teams I start with times 1/2 to the round. So if we started with 32, right, then after one round, you've chopped it in half and you're down to 16, right? And then we chop it in half again and we're down to 8. So this is a little bit more intuitive way to think of this. Now the question says, well, what's Y as a function of X? This is X as a function of Y. So if you want to switch X and Y, that means you use the inverse function. So this is an exponential function, X as a function of Y, but if I want to swap the order, its inverse is a logarithmic function, Y as a function of X. So it's a little bit easier to sort of imagine this relationship, and then we know we can invert that equation and it would actually be logarithmic. So here you plug in rounds, you get teams, but if you want to plug in teams to get rounds. E says your faucet has been left on and is pouring water into your parabolic shaped sink. What kind of function best describes the volume of water in your sink as a function of time? So this one's a little bit kind of confusing because there's a lot going on here. So they mentioned parabola, that's sort of baiting you into saying quadratic. They mentioned volume, and if you know how to calculate volume, you might be jumping to cubic functions, which isn't a choice. Okay, so let's actually break this down and think about it. So the sink, we're going to assume that the water flows, right? Oops. Out of the faucet at constant rate, okay? So when you turn the sink on, we're not jacking it up and down and changing the amount. We just turn it on and we let the sink fill. So the water is going to go flow out at a constant rate, and when you see constant rate, a line should already be jumping out at you. If you don't see a line yet, well, when the water is flowing out of the faucet, it's in a volume, some kind of, liters. Liters is actually volume of water, and that same amount of volume is hitting the sink every second. So the volume that leaves the faucet is the volume being added to the sink itself. So if that is happening at a constant rate, then this has to be a linear function, because lines have constant slope, and the slope is in fact the rate.